dynamic analysis of amplifier circuits is to analyze what happens to the signal when an amplifier has an alternative current signal input and the result of signal processing. We mainly discuss when the input signal is a small signal, a microvariation signal, the voltage amplification factor IU of the amplifier circuit for the signal, the input resistance RI of the amplifier, and the output resistance RO, etc. The small signal equivalent circuit method is usually used. The teaching objectives of this section are 1. To master the small signal equivalent circuit of the transistor. 2. To use the small signal equivalent circuit to calculate IU, RI, RO. 3. To be able to complete IU, RI, RO measurement experiments. Microvariation refers to small changes in alternative current signals. When the input signal is relatively small, if the static working point of the transistor is appropriately chosen, and the input Vout and characteristic curve of the transistor can be considered a straight line over a small range, this linearizes the transistor, which is essentially a nonlinear component, making the amplifier a linear circuit. An equivalent circuit of the transistor is shown in the figure. The connector C of the transistor and the emitter E are equivalent to a controlled current source, beta IB, using input resistor to equivalent. Between the base B and the emitter, the input resistance of low-frequency, low-power transistors is commonly estimated by the following formula. RB equals 300 plus 1 plus beta 26 divided by RBQ. It is particularly noted that the RBE value of a small power transistor is about 1K. A small signal equivalent circuit of the transistor is only suitable for dynamic alternative current small signal analysis. After understanding the small signal equivalent circuit of the transistor, let's analyze the dynamic situation of the amplifier circuit. First, draw the alternative current equivalent circuit of the amplifier. For the alternative current path, if the internal resistance of the direct current power supply is very small, then the alternative current voltage drop across it is very small. It can be considered as a short circuit. If the capacitor is passing alternative current voltage drop is very small, it can be considered as a short circuit. An alternative current path of the common emitter amplifier circuit is shown in the figure. Based on the alternative current equivalent circuit, we only need to equivalent the transistor to obtain the small signal equivalent circuit of the amplifier, as shown in the figure. Now the equivalent circuit is a linear circuit. Analysis can obtain 1 voltage amplification factor, IU. Voltage amplification factor refers to the output voltage U of the amplifier, and the ratio of the input voltage UI, IU equals 0 divided by UI. For the figure, apply Kirchhoff's theorem, and considering the direction of the current, we can get IU equals minus ICRL divided by IBRB, IBRL divided by IBRB equals minus beta RL divided by RBE. The negative sign in the equation indicates that the output voltage is out of phase with the input voltage. The common emitter amplifier circuit is an inverting voltage amplifier. RL equals RC divided by RL, called the alternative current total load resistance of the amplifier. 1 input resistance. Looking into the signal's input end, excluding the signal source, amplifier can be considered as an equivalent resistance, that is, the input resistance of the amplifier. This resistance is the load of the signal source, defined as Ri equals Ui divided by I. The larger the input resistance of the amplifier, the smaller the current drawn from the signal source, the closer the input voltage provided by the signal source to the amplifier is to the electromagnetic force of the signal source, especially when the internal resistance of the signal source is larger. A larger input resistance of the amplifier is more desirable. It can be said that the input resistance of the amplifier is a measure of how much the amplifier attenuates the signal source. Strength of attenuation. For the figure, R equals RB divided by RBE to output resistance. Output resistance are equivalent resistance looking into the two ends of RL. For the common emitter amplifier circuit in the figure there is R approximately equals RC. Let's do an experiment next. Testing of a single tube amplifier circuit. The test circuit is shown in the figure. Experimental content. 1. Adjustment and measurement of the static working point. 2. Measurement of the voltage amplification factor. 3. Observing the effect of the static working point on the output waveform. 4. Measurement of input and output resistance. Measurement of input and output resistance. 1. Based on the measured dosage I and the known R value. Using the following formula, the size of the input resistance I can be obtained. 2. Based on the measured output voltage O when the load is open-circuited, and the output voltage RL measured after connecting the load UO. Using the following formula, the output resistance RO can be found. Now, let's conduct the test experiment of the single-tube amplifier circuit on the experimental platform. Insert the circuit board into a test bench. 1. Adjustment and measurement of the static working point. Connect the circuit on the experimental circuit board according to the circuit diagram. That is, connect holes 3 and 5 with a wire. Connect holes 4 and 5. Connect holes 5 and 6. Connect holes 7 and 8. Connect holes 9 and 10. Connect holes 10 and 11. One end of the signal generator output is connected to hole 1 through a 2K resistor. The other end is connected to hole 2. And connected to oscilloscope. After checking for no errors, connect to a 12V direct current power supply. To adjust the signal generator frequency 1 kHz, a sine wave signal with an amplitude of 20 mV is applied to the input end of the circuit. As the signal source voltage, connect the oscilloscope to the output end of the amplifier circuit. Adjust the potential MRP so that the output waveform on the oscilloscope is not distorted. And turn off the power of the signal generator. Measure the static working point at this time. Disconnect hole 7 and 8 and connect to a digital direct current emitter. Measure ICMA. Record in the table. I'm measuring the voltage amplification factor. 1. Turn on the signal generator. Input 1 kHz. A sine wave signal with an amplitude of 20 mV. Output end is open-circuited. Use an alternative current millivolt meter. Measure the size of and respectively. And record in the table. Note that the alternative current millivolt meter measures the voltage value as the RMS value. When recording, multiply by √2 and calculate according to the formula. To the amplifier circuit is connected to a 3K load resistor connected to holes 12 and 13. Keep the input variation changed. Measure at this time. Record in the table and calculate the voltage amplification factor at this time. Analyze the effect of the load on the amplification factor. 3. Observe the waveforms of and with an oscilloscope. Compare their phase relationships. It can be seen that the input and output are out of phase. Observing the effect of the static working point on the output waveform. Apply a sine wave signal with a frequency of 1 kHz to the input end of the amplifier circuit. Adjust so that the output is an undistorted sine wave. Set the resistance of the potentiator RP to the maximum. At this time, the static current decreases. Use the oscilloscope to observe whether the output waveform is distorted. Draw the waveform at this time. It can be seen that cut-off distortion occurs at this time. To set the resistance of the potentiator RP to the minimum, at this time the static current increases. Observe the changes in the distortion of the output waveform. Draw the waveform at this time. It can be seen that saturation distortion occurs at this time. IV measurement of input and output resistance. Calculate the input and output resistance based on the measured data. List and organize the measurement results and the actual measured static working point. Voltage amplification factor, input resistance. Compare the values of output resistance with the theoretical calculations. Take a set of data for comparison. Analyze the causes of errors. In the experiment, some students often make mistakes. Inaccurate data, mainly due to not taking the operation seriously enough. A lack of strong sense of responsibility in dealing with science. We must be truthful and realistic. At the same time, we must be dedicated to our jobs and loyal to our duties. The content of this class ends here. Goodbye, classmates.